Başlıyor mu? Tamam. Hocam net. Good morning. The second keynote speech of the last day of the conference will be delivered by Professor Fabrizio Paolacci. Dr. Paolacci, do we have a connection? Dear Fabrizio, can you hear me?
Yeah, perfectly.
Okay.
Thank you.
Let me first introduce you and then we will move on to the presentation. Dr. Fabrizio Paolacci is an associate professor of civil engineering at the University of Roma Tre, Department of Engineering. He received his undergraduate and PhD degrees from the University of Rome, La Sapienza. He was a visiting scholar at UC Berkeley in 1999. And between 2008 and 2013, he was in charge of the Laboratory of Testing Materials and Structures of the Department of Structures at the University of Roma Tre. He is currently the chair of PVP Division, Seismic Engineering Technical Committee of the American Society of Mechanical Engineering. He has tremendous experience in the management of international research projects about experimental and numerical assessment of the seismic response of civil and industrial structures. His main scientific interests focus on performance-based design of steel-concrete composite bridges, assessment and reduction of the seismic risk of reinforced concrete building and bridges, seismic risk of major hazard industrial plants, and applicability of innovative protection systems, seismic vulnerability of high-voltage electric networks and substations, and applicability of innovative seismic protection systems, passive and semi-active control of structures. He authored more than 100 publications on international peer-reviewed journals and conferences. We were together in Rome just before the conference started last year for a project meeting. My dear friend Fabrizio, the floor is all yours.
Thank you, Bülent, for the kind presentation. So it's really a pleasure to be here. So, of course, this is a very good occasion to speak about a topic that typically is not well recognized in the seismic field. So before starting, let me thanks also my research team for the strong support that I received in developing most of the topics of today. Okay, this is the problem statement concerning the main issues in seismic analysis of major hazard industrial facilities. So the past earthquakes demonstrated the high vulnerability of hazardous facilities, especially petrochemical plants, against natural hazards, leading, of course, as you know, huge economic losses, injuries, and fatalities, beyond unrecoverable damage of the environment. So we are speaking about of 5% of industrial accidents involving release of dangerous substances were triggered by natural hazards. Earthquakes are the major NATEC hazard for petrochemical plants. So in conclusion, seismic vulnerability should be included in major hazard process plans for risk assessment. And I would like to speak about the main issues involved in this topic. So these are only some examples of NATEC events occurred during catastrophic earthquakes from Northridge 1994 to Tohoku earthquake in Japan, including, of course, Kogeli earthquake that was very, let's say, instructive beyond highly dramatic. Concerning, for example, the Tohoku earthquake in 2011, and according to the questionnaires of Fire Disaster Management Agency, so a lot of facilities were damaged due to the earthquakes, about 3,000, or that represent 1.6% of the total survey hazardous materials facilities. And on the other hand, about 2,000 ASMA facilities were damaged also by the subsequent tsunami. This means a lot of damage like the one that you see here with the oil leakage in many facilities in the east coast of Japan. As you can see here, the most famous accident was in the Chiba refinery, as you know, and as shown in the picture. Beyond, let's say, the clear need to take the problem of setting up methodologies for NATEC risk assessment, let's say some additional problems have to be faced. Let's say there is a general lack of specific rules and standards, lack of specific risk assessment methodology for hazardous plants, some inconsistencies in seismic hazard assessment approaches, and also the fragility estimation for hazardous equipment are not good enough. Finally, there is a very important aspect that is the high multidisciplinary character of a quantitative risk assessment that includes structural engineers, geologists, chemical industrial engineers. That makes the matter rather complicated. There is also an additional problem that with my colleagues we call the communication problems, because the technical communities have different backgrounds, practice and perspectives. So the interaction between several scales need to be captured, including macro scale like seismic assessment, of micro meso scale like structural engineers deal with, and also meso macro scale as chemical engineers are deal with. To simplify this aspect, there are at least two levels: component levels, from which the methods for structural engineers are typically required, and the system level, from which methods for process plant safety analysis are required. A general lack of specific rules and standards on this matter can be noticed. In Europe, we have the so-called Seismic Directive that explicitly consider natural hazard as the triggers for industrial accidents, but without providing specific guidelines to perform seismic risk assessment of industrial facilities. In USA, there are some guidelines, as you know, for seismic evaluation of petrochemical facilities, but provides design rules rather than criteria for risk assessment. Also in Europe, we have a Eurocode Part 4 that actually does not cover adequately measure hazard process plants. And international standards like API 650 or ASME B31.3 deal with the subject only partially and are limited to, let's say, a few types of component like storage tanks or piping systems. Let's say all these difficulties are generate, let's say, prudent attitude among designers. For example, to comply with the Seismic Directive, the PGAs artificially increased by applying the importance factors, leading to extremely safe and conservative design. But this implies the use of dissimilar important factors across Europe to generate a general, let's say, inconsistencies in terms of risk. So as a result, we have no uniform risk design levels for industrial plants, and this can generate some inconsistencies or inconsistent degrees of conservatism and design margins. So we have to clarify this aspect. To complete the overview, I need to highlight the, let's say, inadequacy of existing quantitative risk analysis of process plants for natural hazards. Codes and standards that include civil structure and nuclear power plants actually cannot be directly applied to industrial facilities. So in this way, we need to conclude that an effective methodology to perform quantitative probabilistic seismic risk assessment of process plants is needed, including some relevant aspects that I would like to describe. So to better understand what are the main issues in seismic risk analysis of a non-nuclear power plant, let me start from a nuclear power plant, just to understand the differences. In nuclear power plant, the conditions is typically peace. So we have the main event, that is a core melt, and the main critical components can be identified using 4 trees mainly. And these can be of some help to identify mitigation strategies. In case of non-nuclear power plant, the situation is really different. So in this picture, the red dots are the equipment that are damaged by directly by the earthquake, that can generate in turn physical effects like overpressure, fire, that can hit in the another level, the yellow one, other equipment, and so on, generated in the dynamic way chains of accidents that cannot be predetermined in advance. And all these means that we have the development of domino effects. In this slide, so I have synthesized the key aspects of a quantitative risk assessment. I introduced this very well-known integral in which we can recognize at least two levels: the component levels, that is mainly treated by structural work, in which we recognize natural hazards, seismic demand analysis, damage analysis, and the industrial chemical world, the so-called system level, in which we have loss analysis, consequence analysis, domino effects, and evaluation of scenarios. And you can recognize the main, let's say, parameters that we have to include in the analysis. Let me start with so describe the several aspects, including this integral, and I can start with the seismic characterization. As you know, adopting the performance-based seismic engineering, we have to necessarily identify the performances. But what are the performances for process plants? So we can start from the experience in nuclear power plant, in which there are at least two recognized limit states, so-called design basis earthquakes and safe shutdown earthquakes. The problem is to identify the return period associated, so the earthquake probability. So how to calculate this probability of occurrence related to these two limit states. So this comes from a very reliable risk assessment methodology that so far is not available. So other relevant aspects concerning seismic hazard, so there are listed here. So what kind of motion prediction equation should be used? For example, only let's say local ones suggested for nuclear power plants, or ones derived from a wide regional area. Moreover, a more accurate assessment of seismic effects should be accounted for, because simplified approach presents some highly underestimation of them. And also, the particular attention should be paid on high vibration periods, for example, for convective motion or liquid storage tanks, that could represent a serious problem in the hazard assessment. And also the reduction of record-to-record variability in selecting and scaling the natural records represents a serious problem for industrial components, when typically multi-frequency behaviors is usually present, like, for example, in the tanks. So what kind of scalar or vector intensity measure should be used to scale? So this is an open issue. Let me move to fragility analysis of equipment, in which that is traditionally expressed in the form of demand fragility. Fragility curves, like the formula here presented, in which we can recognize main issues. First of all, the definition of a problem numerical model of equipment account for all possible non-linearities and typically present in the case of earthquakes. Then we have the definition of hazard consistent input signal selection for the assessment of a nonlinear response, and also the selection of proper intensity measures. Also, the selection of representative engineering demand parameters and engineering demand parameter consistent damage states. Along with, we need to identify the corresponding limit states. Also, of course, there are libraries of fragility curves that can be used in the risk analysis that comes from from the experience from the surveys, for example. But the problem is it is possible to use them, or we need to perform numerical simulation of idealized equipment. So this is typically not well recognized, and we need to focus more on this aspect. Fragility curves also are not available for many equipment like pipes, for example, or process vessels or heaters. So this is a problem. But also the degradation phenomena typical of the industrial plants, in which the harsh environment is can generate degradation phenomena need to be accounted for. So the recognize of equipment classes, structural classes, let's say, based on equipment typologies has been recognized in the literature. For example, in this paper that I published with some of my colleagues, in which we identified some structural typologies, critical equipment associated, and typical seismic observed damages with possible additional damages like this. For example, for the tanks, we can recognize very well-known effects in terms of buckling or in terms of uplifting or problems in the floating roof, for example. So the framework is clear, and it's very clear that more need to be done, especially where the dynamic behavior is complicated by interaction, for example, with secondary elements. Recently, we performed shaking table tests in EU Center in Pavia, in which there was a multi-story frame, including that was designed, including some process equipment like storage tanks, pipes, and we recognized, for example, problems in terms of local problems like in the flange, in the pipe flange, for example, in which the leakage could be very important, and also the interaction with secondary elements, in which the floor spectra derived using current codes are not reliable for performing risk analysis. So seismic damage, of course, can induce, as you can imagine, loss of containment. And concerning these, three main issues should be considered. First of all, the relation between the loss of containment and the related seismic damage. That is not well recognized aspect in the literature. The identification of critical chains of accidents associated to this, and the identification of target equipment vulnerability able to propagate these chains of accidents. So typical loss of containment, for example, as you can see here in the table, can be identified based on industrial field, like instantaneous release of complete inventory or continuous release of complete inventory in 10 minutes, for example, like constant rate of release, and so on. So we try, in our experience, to get this definition and to include these in the evaluation of fragility. So, but the problem is that we need more experimental tests for the evaluation of this loss of containment that currently is very limited. And also we needed to have analytical models for the analytical evaluation of loss of containment for the risk analysis. We did some experimental tests. For example, in this paper, you can see some nice experimental results in the use of fiber sensors for the loss of containment detection. How to deal with the problem? So in the literature, there are very limited contributions. So we, with my research group, we propose some damage states, loss of containment matrices like this, in which, according to some damage states and recognize some engineering demand parameters and limit states, we identified some standard loss of containment events, like the one that I showed you before. For example, if you have elephant foot or diamond-shaped buckling, it is possible to have some small release, like lock 1, lock 2, sure. And we include here an on-off, let's say, identification, like yes or not. Not surely instantaneous release of full content. So, and this matrix can help us in identify the type of loss of containment and with the consequences that can be derived using classical tools of classical quantitative risk analysis procedure, like event 3. Now, using the event 3, you have the loss of containment and the release with the quantity of material release, and you can follow, of course, the path for the generation of physical effects, like bushfire, vapor cloud explosion, and so on. And according to these, it's possible to derive the effects on the yellow point that I showed you before, the equipment at the subsequent levels. These are typical matter of chemical rewards, of course, that have to be borrowed to be included in the risk analysis. In these slides, I synthesize the domino chains propagation effect that can be modeled using two different approaches. Using probit function that I use to derive the probability of damage to the intensity of physical effects. For example, when you have, for example, the intensity of thermal radiation, you can go inside the probit function database, and you can evaluate the probability of damage. According to this, you can generate possibly another lock event, and based on event 3, you can go ahead. Otherwise, it's possible to use conventional damage zone approach, where the conventional threshold of effect intensity is reached. So this picture synthesizes the first approach that we use. There is an exhaustive list of quantitative seismic risk analysis that has been proposed in the literature. Here are listed. Let's say, non-actually exhaustive list. There are some others, but here I focus on the most interesting one, in my opinion. And there are also some software that can be used to evaluate these. But the problem is that there is to be more to include all the aspects that I mentioned before, because in each of the several methodologies, some problem is not treated in a satisfactory way. So there is need to include all possible reliable procedure to solve the issues that I showed you before. For example, my research group focus on Monte Carlo simulations approach to develop a software. This is a Priamus software that is in the beta version that has been developed in MATLAB, that is able to generate damage scenarios with the related probability of occurrence, and to evaluate also the domino effects, and finally to include the risk in terms of injuries or economic losses and so on. So it is very flexible approach, but very computational demanding. This is have to be declared. But let's say there are several aspects that have been included in this procedure to solve most of the issues that I mentioned before. So what we can do for the future in quantitative seismic risk analysis. We need to identify multiple starting scenarios deriving from simultaneous earthquake interaction with separate equipment. And this is difficult to be accounted for. Structural damage should be reliably correlated with loss of containment events, as I mentioned before. And this has to be really clarified, especially in terms of experimental analysis. and the modeling. Also, the propagation effects need to be included in a smart way. Monte Carlo simulation seems to be a quite easy way, but we need to, let's say, reduce the computational effort. There are several possibilities, of course. Multiple simultaneous interacting chains of accidents have to be accounted for, and many others, including uncertainty propagation, for example. Currently, the risk assessment model that include all these required features are not available yet. Of course, other future technical issues are, for example, the superposition of the effect from exposure to multiple sorts of events, overpressure, thermal radiation, fraction projection, and so on. That is not, it's really difficult to be included, but also the cumulative damage for superposition, of the seismic input and other physical effects. And this is a matter of, this is a very complicated matter to be included. But, you know, and we need to make more effort in this respect. So let me conclude my speech that I hope has been clear. So the process plan to require different quantitative seismic risk assessment methods with respect to nuclear plants of steel structures. And the two words, chemical and structure, and the seismic engineer word, must talk. This is a must. Multiple starting scenarios and simultaneous interacting chains of accidents should be modeled in a dynamic manner. Monte Carlo simulation allow to do this, but many other possibilities have to be explored. A novel automatic method to systematically generate starting scenarios and keep track of accidents are needed. Once again, Monte Carlo simulation seems to be solved many of these problems, but some computational problems need to be solved. Also, reliable information about equipment fragilities and damage states needs to be investigated more, and also credible correlation between damage and loss of containments are also needed. The open issues are, in my opinion, how to manage piping systems, equipment in multi-level structures, and superposition of damage effects. Let me conclude with these news. So there is a new working group in the European Association of Earthquake Engineering that is coordinated by me and coordinated by Professor Christoph Gutenberg, in which my Turkish friends are also included. So that I would like to thank very much. There are many activities to be developed inside, and I hope that this can stimulate interest of the scientific community on this topic. Thank you very much for the attention.
An industrial plant.
Thank you.
Let's hear from the audience if there is any questions. Yeah, we've got one question here.
Yeah.
Thank you for your presentation.
By the way, just a second, please. Dear Fabrizio, this is a large auditorium. Don't think that the auditorium is empty. The people the people prefer sitting at the back of the auditorium. Okay, it's full. Okay, please go ahead. Please.
If I understand correctly, you mentioned the superposition of the exposure effects.
Yeah.
But uniform hazard spectrum is uniform hazard spectrum providing that, or I assume you mentioned different effects. The uniform hazard spectrum will do the job. Why you mentioned that
So when I mentioned the superposition of effects, so I was mentioning the effects generated directly by the Earth. And of course, using these, you can use uniformity spectrum to select records and generate fragilities and evaluate the damage. But also there are effects, secondary effects, for example, the one generated by the physical effects, including overpressure or thermal radiation, and so on. And this is a typical, let's say, multi-hazard or better multi-risk analysis that need to be included in a reliable methodology. And actually, there are no clear approaches to solve the problem. So I hope to have been clear.
Thank you.
You're welcome.
Any other questions from the audience? Well, Fabrizio, I have one question before we call it off. You have pointed out that there are 3 steps in designing an industrial plant. It starts with determining the seismic hazard. Yeah. Then we need to design each component to meet some certain performance objectives. And the last step is to evaluate the overall performance of the system. The component test or component design requires structural analysis. Do we need any other additional structural analysis to check the overall system's performance, or do we need to take some constructive measures to make sure that the system is meeting some certain performance criteria?
Yeah, you're perfectly right. So the problem is that these, unless you have simple elements like, let's say, like tanks, but not simple actually, but there are many complicated structures like the one that I showed you before, the multi-story frame, in which you have several components that are interacting between them, and recognize damage states and recognize design procedure, right? Design procedure, including all these effects, is a challenge. And in my opinion, we need to do more effort in solving this problem. The experimental test that I showed you before, the SPIF project in Mayo Center, try to answer some questions, but we are still studying the results that are not easy to be interpreted, especially in terms of, let's say, design rules that we should be suggest for improving, for example, the approach.
Okay, thank you.
You're welcome.
Any more questions? I think we don't have more questions, dear Fabrizio. I would like to thank you very much on behalf of the organizing committee and all the participants for your contribution to this conference. Grazie mille, dear Fabrizio.
Thank you.
And hope to see you soon in person in Istanbul or in Rome.
Hope.
Yeah. Okay.
I really hope to visit the beautiful city of Istanbul. Thank you.
Thank you. Bye-bye.
Thank you. Bye-bye.
Evet, ikinci ve son davetli konuşmamıza geçebiliriz herhalde. Sistem hazırsa arkadaşlar. Tamam. Peki. Selçuk Hocam hoş geldiniz. Ben kısaca sizi tanıtayım, ondan sonra isterseniz başlayalım. Good morning again. This is the third keynote speech of the last day of the conference. Thank you. And the keynote speech will be delivered by Professor Selçuk Toprak. Dr. Toprak is the head of Geotechnics Division of Civil Engineering Department at our university, Gebze Technical University. Following his graduation with BS and master's degrees from Boğaziçi University, he completed his PhD at Cornell University in the United States in 1998. He worked at U.S. Geological Survey as part of the earthquake hazard team for almost 3 years, and he started his academic career at Yıldız Technical University. He conducted research international at National Institute of Advanced Science Technology and Waseda University in Japan, and Cornell University, his alma mater. He has collaborations with researchers in more than 10 countries. He is a well-known expert in geotechnical earthquake engineering and lifeline engineering, related to which he authored and co-authored more than 100 scientific papers. He is one of the first developers of CPT-based liquefaction triggering relationships, and he co-authored pioneering publications related to pipeline damage assessment and loss prediction methods. It's my honor and privilege to present my dear friend, Dr. Toprak. It's all yours. The floor is all yours, Dr. Toprak.
Thank you, Chairman. Dear Bülent, for the introduction. Welcome, and today my keynote speech will be about seismic resilience of lifeline systems. I like this particular term, lifeline, because it reminds me, it resembles the human body and the connection with the urban areas and society. Like the blood circulation system in our body, digestive system or nerves, actually the transportation systems in urban areas, lifeline utility systems, including potable water, wastewater, oil, natural gas, electric power, communication, they all provide life to our cities. And some researchers include solid waste management also in lifeline systems. If we include or not, it doesn't matter, because it is a part of the urban societies, and we try to tackle this issue with different projects. Lifelines can be extended through long distances or can be networks in the cities. In the left figure, we see the natural gas and oil pipelines in Turkey extending from east to west, north to south. They may also extend across the countries as well. They may be part of the cities, like the one shown in the right figure, for example, the water supply system. I like this particular figure in the sense that it shows the full view of Lifeline's resilience model. You can find detailed information from my colleague Craig Davis from Los Angeles Department of Water and Power. He's retired now, but he has very good presentations, particularly on this model. But I will only use the salient features relevant to my talk here. On the vertical axis here, sorry, I think there is a problem with the pointer, but on the vertical axis here, we have the systems I mentioned as lifeline systems. On the horizontal axis, we have the hazards, and then on the other axis, we have the event cycles. Now, within this frame, actually, we need to consider all hazards and multi-hazards all together or individually. And we need to take care about the project life cycle additionally. Now, if we focus on this particular cubic that includes one particular hazard and then one particular component of the adverse event cycle, we need to tackle again several dimensions. One can be related to social, economic, technical, or organizational issues, and also it can incorporate resilience properties like redundancy, rapidity, resourcefulness, robustness. But in any case, we need to consider different event cycles like planning and preparedness, mitigation, response, recovery, and rebuild. In that respect, we also need to take into consideration risk and uncertainty. When we talk about resilience of lifeline systems, we always deal with some uncertainty and also deal with different levels of risk. Maybe we'd better define some of the parameters we use in the resilience model. For example, robustness. It represents inherent strength and resistance in the system. Redundancy, system properties that allow for alternative options, choices, and substitutions. Resourcefulness, capacity to mobilize needed resources. Rapidity, speed with which disruptions can be overcome, service, income, etc. restored. As I mentioned, we can deal with multiple hazards, all hazards like floods, tornadoes, climate change, or maybe we may focus on a particular hazard like earthquake. And the topic of my keynote speak today will be mostly related to seismic issues. There are lessons to learn from each disaster regarding several components of seismic resilience, such as planning, mitigation, response, recovery, and rebuild. We also need to consider strong relationship among those events. In that sense, actually, I have to point out that when you invest in the initial ones like planning, preparatory stages, and mitigation, actually you save from the last two items, maybe recovery and rebuild, including response. Because by investing on planning, actually you determine your weak points and then you mitigate them. So you are ready for the disaster and you spend less in terms of money, in terms of time, in terms of effort, in terms of casualties in the rebuild and recovery sections. So this is a decision we have to make. We wait for the event to occur and deal with the consequences, or we prepare for it and be ready and diminish the consequences. Well, I will take here three particular cases that we worked in the past. One of them is Canterbury earthquake sequence from New Zealand. It was a special case. It involved 4 relatively significant magnitude earthquakes occurred one after another, as you can see on the screen. And you can imagine how devastating and damaging can be such consequence events together. Well, one important feature that we take out from Christchurch, it was the extent of the liquefaction. You can see in these figures, particularly the extent of liquefaction, and this is not only for one region. This figure clearly shows the extent of the liquefaction zone in Christchurch. Actually, a significant or most portion of Christchurch experienced some level of liquefaction in itself. Well, on the same figure, I showed the pipeline repairs here, and you can see them in more detail in this figure, where we characterize them with respect to pipe material. And we can clearly say that actually liquefaction had adverse effects, large damaging effects on the pipeline system. Well, those damage assessments are very useful for us because the results we obtained from those damage assessment, the models, the approaches we develop actually help us in planning and preparedness stages. It also guides us through the mitigation stage because by using those results from the damage assessment studies, we can determine the weaknesses in our own system. Here I only provided some examples on the figure. In the figure on the top left, I plotted, when I say I, of course, we worked on this, research as a group. Maybe I should say we plotted or in our studies the correlation between the repair rate, which represents the pipeline damage rate in the system, with one of the seismic parameters. Here we refer to geometric mean peak ground velocity. It actually represents the effect of seismic waves while they are passing nearby or around the pipelines. In the figure on the left bottom part, actually we can see the pipeline damages or damage rates caused by permanent ground deformations. And we characterize those permanent ground deformations in terms of lateral ground strains and angular distortions. Because we need to determine the ground effects on the pipelines as well in our damage assessment studies. As I mentioned in a summary from this page, I can say damage assessments directly help us in planning and preparedness and mitigation stages of resilience in lifeline systems. This figure also shows the state of the repairs. In other words, recovery process during when we try to obtain when we try to get to performance levels that we had before the earthquake. It's very important, to get the original levels or the levels before the earthquake. The sooner actually shows your, resilience capacity to respond to disaster. Well, this figure shows that actually right after the earthquake, we have a steep slope that shows initial frequency of repairs is quite high, and then we have a transitional frequency of repairs, and then we reach the post-earthquake steady state frequency of repairs. These figures actually show the recovery stages after different events I showed you in the beginning of my presentation. But in any case, please have a look at on the figure on the right bottom. This figure actually with the green lines shows the average repairs in the system before the earthquake. In our cities, each day actually we have some kind of repairs made to the system. Some failures occurs and some repairs are made as a result of getting back the system to the original level. But figure shows us that after the recovery stage, it takes considerable time to get to the original levels. Still, several months pass, and we are having higher repairs per day compared to average levels before the earthquake. Second example comes from Simmons Island earthquake we had actually in October 30, 2020. So the source of the earthquake was about 70 kilometers away from the Izmir city, and it caused, unfortunately, around 150 casualties in Izmir. It also affected Greece side and Turkish side together. The area was highly populated, and different large lifeline systems, including water, wastewater, natural gas, and electricity, was serving in this area. And we were lucky in the sense that actually the highly populated region of the city was quite far away from the source of the earthquake. As I mentioned, it was about 70 kilometers away, and the most damage occurred in Karşıyaka and Bayraklı area, where we have some site amplification effects. Following the earthquake, the electric and gas services to about 74,500 and 3,000 subscribers respectively stopped. The restorations were quite fast, as I said, because the distance between the earthquake source and the city, the attenuation actually contributed to the low levels of intensity in one sense, although we have some damages at local areas as shown in the figures at the bottom of the slide. Because of those failures, actually, the gas restoration and electricity restoration to certain areas was not possible, because you need to make sure that actually it will not cause any additional problems in the area in terms of, for example, gas explosions. And the figure on the right top actually shows the recovery line for this electricity system in Izmir. Starting from 74,500 subscribers, it get back to about 251, and all those actually were destroyed or damaged buildings. So this actually showed us in a small scale that the interaction between the systems is very critical. And here the quality of the structures especially play an important role in the performance of lifeline systems. Also, in Seferihisar, we had some electricity interruptions because of the tsunami effect. The transformer substation, L37, which was damaged by tsunami, re-established about noon of 31st October, and then electricity was able to supply to the 435 subscribers. Again, this was an tsunami at very small scale. And we have seen in the world much larger scale tsunamis from Japan, from Indonesia, and in the figures on the top, I show some pictures from Japan. You see the houses moved, ships moved, and industrial facilities get damaged. Actually, all nuclear power plants were shut down following the Fukushima nuclear power plant disaster in Japan. But in Seferihisar, we had only the furnitures floating on the surface. Unfortunately, we had one life lost in that one, but it was a warning for us to get ready for much larger tsunamis around our cities. The third example comes from Los Angeles water supply system as a result of the effects from 1994 Northridge earthquake. And in this system, it is a large system, and there were about 1,000 repairs to distribution systems and 74 repairs to large diameter system, water supply system, which kind of interrupted the service in the city as well. On the figure on the right side, we have actually repair rate distributions of damages superimposed on peak ground velocity, and where we can see actually damages concentrated on particular areas. And those concentration areas also related to geotechnical, particularly geotechnical issues. As I said, part of the resilience is recovery here, and then when we look at the performance versus time in Los Angeles water distribution supply system, we see actually different performance levels were achieved, but functionality, to get back to functionality to 100%, actually took much longer. Well, we have two ways to proceed at that level. One is proactive management. The other is reactive management. You know, in the reactive management, you just wait the event occur, to the disaster occur, and then you say, okay, now I will do whatever I can do. But this is not what we want, actually. In that case, depending on the extent of the disaster, you may be kind of a hopeless situation, or the recovery may take much longer than expected. The one we desire is proactive management. So in proactive management, actually, you take precautions, you do the planning, you take the preparatory actions and necessary mitigations so that you reduce the effect of the disaster. And to do that, you need proper tool and expertise in analyzing the lifelines as a component and as a system. And here we need to take into account seismic demand, pipe capacity, and consider different deformation modes in the system itself. This can be a pipeline system, this can be a transportation system, and any lifeline system can be analyzed by using different tools. And especially if you are dealing with the ones which are some connection with the soil, like buried pipelines, then you need to consider soil structure interaction by using different analysis tools. I just showed a few of them here. Analytical tools can be finite element tools and finite different methods. And these figures actually shows what we don't want to have in our system after the earthquake. The one on the top left actually from a wrinkle at water pipe in Turkey because of the Kocaeli earthquake, and the other figures are related to pipeline performance in Balboa Boulevard in Los Angeles after 1994 Northridge earthquake. And these figures are from 1995 Kobe earthquake. Again, it shows what we can have and what we don't want to have after our earthquakes. And these figures shows the failures after Christchurch earthquake. Well, we have a problem. We have an aging infrastructure issue in Turkey, actually around the world. So how to deal with this problem, how to deal with such a large system already existing. So, and also it is aging. These figures are from replacement study in Denizli, and you can see the status of the pipelines. To some extent, they are cleaned actually, and the current ones underneath the cities are not so different than the ones shown in the figure. Well, in the first day of the conference, Professor Jonathan Bray made a presentation about the performance of foundations in liquefiable soils. And he, proposed, or he and his team proposed some solutions, some analysis techniques, considering different parameters, different indexes. And also, we use similar approaches to assess the damages to lifeline systems and make them relevant to mitigation studies and also, planning stages of all resilience models. And in that respect, we created models using the pipeline damage and liquefaction severity parameters like liquefaction potential index and liquefaction severity number. Just to refresh your memories, I provided the definitions in this slide, and LPI is used significantly in liquefaction hazard mapping proposed by Iwasaki et al. 1978 and 1982, and we calibrated it in 2003 when I was working at US Geological Survey, and it is commonly used, as I said, in liquefaction hazard mapping studies. And we know that many cities in Turkey or around the world already had some liquefaction hazard map study performed, and they can, to help them combine their existing studies, we worked on the pipeline damages from Christchurch to develop relationships. And we use primarily CPT data and CPT analysis techniques, and we were lucky to have more than 10,000 CPT data coming from Christchurch after the earthquake. And by using those, actually, we were able to develop fragility relationships, as I said, to help planning stages and mitigation studies. And those studies clearly show that different pipelines made of different materials show different performance in the earthquake. And for our case, for example, here, PVC and AC pipelines performed the best and worst, respectively, in all cases, with CI cast iron pipelines in the middle. So those correlations have the potential for use with existing or new liquefaction hazard maps for prediction of pipeline damage from future earthquakes. Well, we need to use new technologies or developing technologies in all our assessment and resilience studies. Here, for example, we utilized remote sensing like satellite information, LiDAR, air photo, all kind of information which, or technology which help us to assess the damage levels and help us actually to improve the resilience of the lifelines. Different techniques are available depending on the situation. We can revert to different ones. For the fault zones, these figures are provided by Mr. Vitali and from the Sakhalin pipeline project. If you have a fault shear zone, then you revert to wide trench, for example, and if you have axial loading expected for the pipelines, you can revert to narrow trench. And also, you can benefit from the different fill materials to improve the performance and different materials like geotextiles at different stages. Seismic isolators are getting quite common in Turkey, and I'm sure you have seen their applications at different locations. In this figure, we have one from Mecidiyeköy viaduct, but we can use it in any lifeline system also, if required. Here, an application for the electricity station, electricity transmission station was shown, and if we want to reduce the effect of the shaking, we can utilize those techniques. if we expect any problems around our lifelines regarding the soil performance, if we have weak soil, it may have some, let's say, liquefaction consequences, then we can apply different soil improvement techniques as required by the loading. And we know that actually our lifeline systems, including pipelines, they are affected by the ground movements, and this can be in any horizontal direction, vertical direction, so we can have rotations resulting in extension and compression in joints of the pipelines. And there are actually applications with earthquake resistance joints, especially in Japan and in US. And also in Turkey, we have some applications of those. Basically, if your analysis in the planning stage shows some kind of large displacements at particular areas of the city, then you can apply these kind of, the pipelines with these kind of joints. They have some extension and compression capacity depending on the model, and you can also get some shear resistance, and also they have rotation angle capacities changing between 7.5 degree to 15 degree. Fiber reinforced polymers, it can be used in bridges and also in pipelines. Structural health monitoring can be used for rapid and continuous condition screening and aims to provide in near real-time reliable information regarding the integrity of lifelines. Now we have different tools actually to increase the resilience of lifeline systems, and we need to be using all these systems. Here, if you follow the presentations, in the first day, actually many presenters expressed their interest in use of fiber optics for lifelines. And I only showed one application here. Along the pipeline, you also place fiber optics so that you can get information regarding the seismicity, ground deformations, and or leakage information, for example. So it is a kind of hot topics in recent years to use all those technologies in lifeline systems to increase the resilience and to decrease such as recovery time if you have any problems. We need to revert to different tests if we are developing new materials, new methods, or sometimes if you want to test existing systems also, we need to revert to these kind of tests. One is centrifuge test. Basically, you apply a high gravity acceleration so that you resemble the real case as much as possible, or you can use large scale lifeline test facilities. And I just showed two examples here, Rensselaer Polytechnic Institute and from Cornell large scale lifeline test facility. You know, in order to get, let's say, performance assessment close to the one in the field, you need to do different tests in that scale. And if you don't have this kind of facilities, or international collaborations are always open, and maybe to advance the science and engineering, we need to bring the forces together to get much better results. Well, we said all resilience models or resilience analysis involves risk and uncertainty. And a simple definition of risk is consequences multiplied by likelihood of failure. Actually, as a human being, it also, maybe from your mind, even though you don't do exact mathematical calculations, you kind of feel actually if the consequence of failure is high, then you behave different, for example. If you think likelihood of failure is low with anything in your life, you behave differently. So actually, your decisions on this likelihood of failure, consequence of failure, brings you from do nothing to low priority, monitor, investigate more, action. This is true for lifeline systems, but we have to do that in a more systematic way and also continuously. Now, we cannot say we did some seismic risk analysis in our lifeline system 5 years ago or 10 years ago, we are okay. No, this is not true. No, this is a continuous process, and we need to get our preparations continuously, and we need to get ready for the next disasters. Well, I want to acknowledge my students and co-authors for the work I presented here. Also, our supporters through different projects, TÜBİTAK and European Union, and also a national agency. With that, I would like to conclude my presentation.
Thank you, Dr. Toprak, for this excellent presentation on the seismic resilience of lifeline systems. We always think that resilience is something that we use for superstructures, but I think resilience also needed for underground structures. And before we move to the questions, I just want to say a simple word on the proactive management system that you mentioned in your presentation. I sincerely think that we need that proactive management system for the above ground structures as well, not only for the underground structures. It's needed everywhere. Yeah.
I think, we need that kind of approach in our life as well.
That's right.
In everything.
Yeah. Thank you. Do we have any questions from the audience? Please, yeah.
Thank you very much for this very, very informative presentation, because there were a lot of things. But my question, I think maybe, and also I'm wondering your opinion on the structural health monitoring system or geo-monitoring system. I think I'm wondering what your opinion is on the use of the structural health monitoring system and the geotechnical monitoring system is, especially for the seismic resilience of the infrastructure systems. This is my first question. And the other thing is, the other question is, I don't know if this is possible or not. Early warning system, yes, we can use the early warning system and for the estimation of the estimation of the earthquake. But is it possible to propose a method not like the early warning system, but is it possible to estimate the aging and other deteriorating things before when we make a decision? Is it possible? I have two questions. Thank you very much.
Okay, I think I tried to hear entirely, but there was some voice loss, I think, during the transfer. But let me say what I understood. Your first question related to monitoring of lifelines, am I right?
Sorry about that, maybe. My first question is related to the monitoring of the civil infrastructure systems.
Okay, I
and
understood.
is it possible, or how can we place the monitoring of the structure, civil infrastructure, on the resilience of the seismic resilience of the structural system? This is the first question. And the other question is, I don't know, maybe is it possible or not, but is it possible, for example, aging of the pipeline system and other structural elements to develop a method like early warning system of the earthquakes like this? This is the question.
Okay. Thank you. I think both questions are very critical, good questions. And, for the monitoring, actually, there are always improvement in the methods and in the techniques we use for monitoring purposes. And for example, the one I showed, those fiber optics, it has been recently promoted in different applications. For example, for leakage applications, for the pipeline systems, because it's very critical. You may have some environmental consequences as well, in addition to fire hazards, etc. And actually, by using those techniques, you speed up, or you get alarmed about a failure possibility, and before it is too late, you respond to it. But some of them, let's say, in development stage, so we need to keep up with the new developments in that sense. Maybe, if some of us actually interested in those techniques as well and working in developing those techniques. And you might remember in the first day here, there was a panel, and in the panel, this was one of the discussions also. For example, Aselsan made some presentations regarding this issue. So there are different government and private organizations in Turkey and around the world working on this particular issue. For the aging of structures, actually, it is similar. There are existing methodologies depending on your lifeline system, because we are talking about a broad system here. For example, transportation systems are also part of the lifelines, pipelines itself also, and pipelines also can be grouped into water supply system. It is different from the gas distribution system, for example. Material-wise, or the precautionary actions taken, because if there is a leakage in water supply system, the response is different than if there is a leakage in gas distribution system. So we are talking about a broad network of systems here. For each one, actually, we need to deal with different issues. In some of them, we use, for example, cameras. You can insert cameras in the system, and then you can take pictures, or you can, let's say, record all the damages there. And in some of them, we use radar techniques to determine how much deterioration occurred, for example, in the thickness of the materials. And sometimes we use waves, like sound waves, and take the response in the system. So there are so many different techniques we could use, and they are still developing. And what I want to express that although they have some limitations, we have some techniques, and we need to utilize them. We are not at a stage that we cannot say that we don't have the tools at the moment. I think we have the tools. We can do our best with the existing ones, and we can help develop the new ones. I hope I answered your questions.
Any more questions? Okay, then before we conclude this session, I also have one question. Do you think the current regulations in Turkey require that a lifeline planning or lifeline structure systems need kind of seismic resilient design procedure, or do we need to change the regulations at national or local level to put the seismic resilience design concept into effect?
Well, most of the regulations we have are related to new ones. You know, if you want to have a new structure, let's say new pipeline system, then you have some regulations. Actually, even some of them came very recently. We didn't have regular or a regulation exactly to respond how to model seismic resistant lifeline systems. But they are coming out, some of them already came, but they are not for exactly to have resilience systems. They don't give answer to the existing ones. So I can, short answer to your question, yes, we need actually regulations in that respect to improve the resilience of our structures.
Okay, thank you, Dr. Toprak. Okay, with that, let's conclude this session, and we are exactly on time and ready for lunch, I think. Thank you, Dr. Toprak, again, for this excellent presentation. Thank you.
It's my pleasure. I thank the organizing committee and Earthquake Engineering Association and all of you being patient here listening to the presentations. Thank you.
Pardon, bir anonsumuz varmış.